Okay, so problem 1439 asks us to find the inverse Laplace transform, but this one, before we can use partial fraction decomposition, and okay, so just a note, since my campus is closed, I'm recording at home, and so you might hear my dogs in the background. So the first thing you have to do with this problem is get it in a form where it's not like an improper fraction. So you have to do long division for that. And I've done it. You don't want to watch me do that, but what I have it right here. And if you don't remember how to do it, just pause the video. You should be able to follow it and then get the answer here. So the quotient is on the top and then the remainder is down here. Okay, so then I can rewrite this function as follows. So s squared plus 6s plus or minus 97, and then this fraction. But notice the denominator, s squared plus 12s plus 35, that denominator can be factored as s plus 5 times s plus 7. So I am just going to do partial fraction decomposition on that part of it. So this will equal a over s plus 5 plus b over s plus 7. And then I would multiply both sides by the LCD to clear denominators. And I'd get 969s plus 3415 equals, and then the a will be multiplied by s plus 7, and the b will be multiplied by s plus 5. And so there are two nice values to plug in. I'll plug in -7 first, so I need my calculator for that. And I get -3368 equals, and then the a is gone, so b times -2. And divide both sides by -2, and you get b equals 1684. And then plug in s equals -5. And then you get -1430. Oops. Equals, and then a times 2, and the b is gone. So you get a equals -715. Okay, so those are our two constants, and so now I can completely rewrite this capital F of S. So A is -715. And then B is 1684. So these last three terms, we can get those just straight from the table and from the constant multiple rule. So I'm going to bring the table. So the term that has the 97 in it, you want to think of that as 97 times 1. And pull the 97 out in front. And then if 1 is the function in the S domain, then its corresponding function in the time domain is that delta of t, delta Dirac, or the impulse function. So function in the time domain is the inverse Laplace of the function in the S domain. Now I'm going to leave some space for the s squared plus 6s. So I would have minus 97 times the impulse function minus 715, and then s plus 5 goes with e to the negative 5t. I'm going to go ahead and just multiply it by, instead of putting the u of t at the end, because it's really just these last terms that will have the unit step function. And then plus 1684 e to the negative 7t times u of t. Okay, so what about the s squared and the 6s? And if you go look at the table for the pairs, every one of them, the s is just in the denominator, except when you get to the ones with the trig functions, but still the degree of the denominator is bigger than the degree of the numerator, so there are always more s's in the denominator. So this table doesn't help at all with the s squared and the 6s. This is where that differentiation in the time domain property comes in. So the s squared we can think of as s squared times 1, and then that would correspond in the time domain to the second derivative of the delta function or the impulse function, but we do still have to worry about these other two terms and see what's going on, the minus sf of 0 prime and the minus f, or not 0 prime, 0 on the negative side minus f prime on the, at 0 on the negative side. So what I want to do is look at, so I'll come back to that in a second. So let's think of if we were taking the Laplace transform of the second derivative of the delta function. So we would get s squared, the Laplace transform of the original, which is just delta t. And remember, the book calls this, and so do all differential equations textbooks, they call that f of s. F of s is the Laplace transform of the original function. Okay. So the s squared times the Laplace of the original, and then minus, remember the powers of s go down by 1, and like the derivatives go up by 1. So minus, now it'll be s to the first. And remember the Laplace transform is defined as an integral, and the derivative of an antiderivative is the original function. So I'd have s delta of 0 on the negative side, and then minus delta prime of 0 on the negative side. So I'm just going to go back to the table for just a second. So here's that notation they talk about up here. Here's the original function and its Laplace transform corresponding to this f. So when they're taking the Laplace transform of the second derivative of some little f, they get s squared, the Laplace transform of the original, minus f of the original function at 0 minus the derivative at 0 minus. So that's what I'm doing here. S, the original function at 0 minus the derivative at 0 minus. Okay, so the graph of the Dirac delta function or the impulse function is, this is the symbol in the book. So if you have the PDF like I do, it's page 35, but in that like hard copy, it's page 18. So see, it doesn't do anything until you get to 0, unless it's shifted. Like see if they have the t minus 1 here, it shifts it to the right 1 unit. So there's nothing, 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 and then this impulse and it goes back. So when we're looking at delta of 0 just to the left, that is like right over here, well, there's nothing. So that part is just 0. And I'm gonna draw it in orange just so you can kind of see it here, because the next thing we need to do is evaluate the derivative just to the left. Well, just to the left of 0, it's a horizontal line. And so the slope is also 0. So this term goes to 0, this term goes to 0. So all we're left with is that the Laplace transform of the second derivative of the delta Dirac delta function is s squared times the Laplace transform of the original, which is just 1. And we could do the same thing for the first derivative. So remember, the power of s matches the derivative you're taking. Second derivative, second power of s. First derivative, first power of s. Of the original. Power of s goes down by 1, so now there's no s. And then the derivative goes up by 1. The derivative of an antiderivative is the original. And we already said that delta to the left of 0 is just 0. So we just get s times the Laplace transform of the delta function, which is just 1. So we just get s. So that helps us with, those are the first 2 terms were all we had left. So where does the s squared come from? Well, in the time domain, s squared came from the second derivative of the delta function. Plus the 6 is a constant you can pull out in front. Where does s to the first come from? Oops. S to the first came from the Laplace transform of delta prime. Okay, so that is it for problem 39. So that should get you through the homework, but I'm happy to help if you have questions.